Okay. Start. Share my screen. Okay, so just to give an outline of what I plan to do. So we have seen crypt key structures as a model both for its transition system plus something, which can not only describe model our systems, includes the transition formalism, but also has these label thing to be describe executions and behaviors. We saw that. We also saw traces. We defined what traces were. There were two kinds of traces: linear traces and branching traces. There are two concepts associated with crypt key structures: the actual behavior, okay, which is the actual behavior, the set of either linear traces or branching traces induced by the set of all legal executions. Okay, an execution is an infinite sequence of transitions from any one of the initial states. Traces are derived from executions. They use the labeling functions, okay, for the states. And the actual behavior is the set of all linear traces that is produced, that is induced by the set of all legal executions from all the initial states. Now, property we already saw informally. It is intended to define your expected behavior, an aspect of your expected behavior. It is formally a constraint defining an expected set of behaviors. Now, these constraints can be, depending upon whether you're interested in linear behavior or branching time behavior, they can express constraints over the acceptable linear traces or branching set of computational trees, and they are expressed as a formula. Okay. Now we'll look at the model checking problem. Now, so just to see what you remember this crypt key structure, correct? It has the transition system plus the labeling function. Now we have, I've indicated to you that we will assume, at least for the purpose of this course, that what we are interested in analyzing only finite transition system, crypt key structures whose universe of states is finite. Okay. Now, I told you that even for infinite state systems, if you, as an aside, I mentioned that if you restrict yourself to a finite set of labels, there is a way that you can kind of abstract an infinite state system as well. But let me get to that. Okay, for a moment, I kind of told you that we will talk more about that. Okay, even if in my comments about how you can get finite labels means that it'll automatically introduces an abstraction which converts an infinite system into a finite system. Even if you did not understand the comments that I made, we'll get back to you. But for the time being, let's assume that our crypt key structures that we care about are finite, in the sense our S, the state S, is finite. Okay. Now, if you assume that our transition systems are finite, what is an impact? I want to make an observation, okay, which is kind of related to probably the question that Ratnakar probably asked last time when I introduced this concept of this witness to a thing. We'll get to that. So, but nonetheless, sorry, this is not what I wanted. Yeah. Can you see this?
Yes, sir. Yeah.
Yeah. So if the set of states are finite, then these are some observations. So a transition relation T, okay, that maps the current state to possibly a set of successor states, has to be finitely branching. Do you agree? If there are only finitely many states in your universe, and your transition relation is mapping a state, so it can only be these branching, it can only be finitely branching. Do you agree?
Yes, yes, sir.
Yes. Okay. Now that is one. Well, for an infinite state system, you can have infinite branching. Okay. The other thing is when you look at linear traces or linear executions, it'll always, every infinite path, you know that we have made transition system to be left total, and we also make this assumption that that there is no terminating states. Okay, so the paths, execution paths, and the traces that are generated by our transition system or Kripke structure are all infinite paths. But if we assume that the transition system is finite, that is, yeah, this universe of states is finite, then every path has to be shaped like this, correct? Because sooner or later, a state gets, repeated. Right? So if you look at any infinite path, that is infinite path, which is an execution of a transition system, will have to eventually have a state that has occurred before. So they all are of this kind. Okay, we look at each. Do you agree?
Yes.
Yeah, yes. Yes, sir.
Yeah. Now, and similarly, computation trees will also be folding back like this. Okay. So yes, it is finitely branching. Yes, at each from each state there can only be finitely many outgoing edges, but eventually you will get to something which you have already seen, and therefore then all the the trees that originate from that is something that you would have already seen. Okay, so this is some observation that you have to keep in mind, and we will since we're restricting ourselves for analyzing and model checking finite state systems, this property will be exploited. This observation will be exploited. Okay, and while we will get to a safety property, let us defining that, and this witness that I kind of mentioned in the passing while during the new SMV demo, and so that the fact that it has to be looping the witnesses, at least for finite state systems, it is certainly true. But that thing is independent. That observation is independent of finite and infinite systems. But nonetheless, let's now restrict ourselves to this observation. Okay, this is something that I wanted to mention. Okay, so the question is then, of course, I've told you that I've introduced you two kinds of behaviors, and those are the kinds of behaviors that we want to study. Dynamic behaviors of the system. So now the question is, so model checking, one component is the model, the other is you have to have a way of specifying the property that you want to check, the expected behavior. And of course, given those two things, model checking is an automatic way of checking if a particular models satisfies a given property. Now, I'm Now asking you a question, how do you formally specify a property? Okay. One can, as I've already shown here, behaviors are structures. If I restrict to linear behaviors, a behavior is a set of linear infinite traces. They are structures, and you have studied first order predicate calculus. One way that you could specify is use predicate calculus over sets of paths. Okay, first order predicate calculus, you can have various structures, maybe functions and other things, and now you can have sets and traces. So you could, and you can, if you want to describe linear properties. A property is a constraint, okay, is a set of behavior. So you can do on paths. For example, this, remember that this thing that we had, the mod counter. Where was that? Of course, if you have linear traces over the mod counter, one of the properties every execution here, starting from an initial state, satisfies is it satisfies this property, correct? So this is the we saw this example as well as the mutual exclusion example. So I hope you remember that. So you could specify, for example, that the mod counter state, every path, execution path from originating from any of the initial states, and then this condition that the value of the counter is less than or equal to 3 forever, can be specified as a constraint on the kind of acceptable paths. So here, so you should read this as a constraint. So I'm just using first order predicate calculus. So you could, first order predicate calculus is very powerful language. So you could say, I mean, any path satisfying this constraint is, I say, is included in the set of acceptable behaviors. What does this say? That I, for every I is the index. Or infinite trace is a sequence of states that has certain labels. So I am using as an index to a position in the trace, and I'm specifying these constraints. For every I greater than or equal to 0, the label of Si has to be L equal 3. Or in other words, what you're saying is your execution traces have to be such that for all I greater than or equal to 0, Si must be the state in Si, the AB counter. It must be less than or equal to 3. So you could use this. So first order predicate calculus is a thing. So for example, each first order predicate calculus is a very powerful language to express all kinds of properties, that are even non-computable functions, etc., can be expressed. So, but we are interested in these kinds of behaviors. Now, if you want to specify as an example that each process enters its critical section, okay, in the mutex example, its critical location CR infinitely often on all executions can be specified this way, okay? So to read these formulas, these first order formulas with quantifiers that I'm introducing as constraints on the paths that are included in the behavior. So for every I, the path should be such that for every index, at every index I greater than or equal to, at every index, for every index on that path or a trace, there must be another position that occurs at or after I, such that sj.pc1, okay, is equal to CR. And similarly, for every I. So what I'm saying is infinitely often means that for every position, there must be a future position at which the process PC is equal to CR. You see? So you could use this. You see the point I'm making? How first order predicate calculus can be used for specifying linear constraints. Yeah.
Yes.
Okay. Now we also saw in that I'm saying here what we'll be using is temporal logic, but I'm motivating it, okay, as to why we will do temporal logic, okay. You could now, for example, we then saw in the mutex example that this condition, the starvation freedom from starvation condition, were true only for a subset of paths. You can even specify that. So here I'm stating that each process enters its critical section infinitely often, only on certain fair executions. Okay, and by fair execution, I mean on those paths in which turn is equal to 0 happens infinitely often, and turn is equal to 1 happens infinitely often. Given that on those paths where this condition holds good, then this that guarantees that PC1 being CR and PC2 being CR will happen infinitely often. So one can use these, first order predicate calculus, okay? But as you can see, similarly, branching behavior also for the mod 3 counter, I mean, you could say that, for the mod 3 counter, for example, here, for the branching behavior also, what I'm saying is branching behavior also can be specified that way. It will be a little bit more complicated, okay? So you will have to say that, or if you want to say something like, if for every state, every path originating from every state, an initial state is such that there exists a path originating from that state on which certain condition holds good. Okay, so for example, in this case, for a branching behavior, I'll be able to see this. So I might want to say that even this is initial state here. So the branching behavior not only includes this tree, but it also includes a tree that is originating from this state. Okay. So if I want to say that there exists an initial state from which there exists a path on which in every state the value of the counter is 0. Okay, which happens to be the case, right? So if you start from the state 0, 0, 1, with the reset is 1, then from that state, and then there is a path. Okay, for example, like this 0, 0, 1, where reset is 1 continuously. Okay, so you could. So for starter predicate calculus, the point I'm making, the limited point I'm making is you could use for starter predicate calculus to do that. But proving things in first order predicate calculus is a hard thing, because first order predicate calculus is very powerful. Okay? And then you can't prove, that first order predicate calculus by itself is undecidable. Okay, so so you can forget about proving things automatically. Then maybe if you restrict yourself to finite state systems, you might be able to do it. But usually, instead of using first order predicate calculus, where it allows the expressiveness is somewhat is very expressive, people look for specialized logics. Okay, and the reason they look for, it's interesting to look for specialized logics is their expressive power is deliberately restricted. Okay, and by restricting the expressiveness, the decidability problem, that is the problem of checking properties in that restricted language, can be not only decidable but also more less complex, more efficient, less complexity wise. And that's the reason that if you're especially interested in automatic methods, then one thing that they do is they look for restricted logics, okay, which are not as expressive as full first order predicate calculus, and even specialized logic, so that then you can exploit the structure, the limited structure of the formulas in that language to devise decision procedures or model checking procedures which are concerned with checking properties in that language. Okay, so there are two ways and that's why model checking looks at either automata which can express certain restricted fragments of patterns of behaviors, or logics whose meaning is somewhat restricted. Okay, so what we will be doing is we will not be using, and we want to make the observation that we could use first order predicate calculus and throw the full power of first order proofs in that. Instead, model checking is concerned with using either specialized temporal logics or special kind of automata to devise automatic methods for deciding a class of properties that are somewhat restrictive in its expressive than the full first order part. Okay, so that with that motivation, I will start introducing. We'll specifically look at start looking at CTL star, which is able to express properties or constraints over these branching time behavior or linear time behavior. And then we'll be looking at two sub logics of CTL star. CTL stands for computation tree logic. Okay? And two sub-logic called CTL and LTL. LTL is able to express only linear time properties. These will be sub-logics of CTL star. And later in the course, we'll also look at automata-based methods, specifically Buki automaton method, Buki automaton as a way of expressing, describing properties, and automata-based model checking methods. Okay, so any questions on this motivation part? Okay. Questions? Let me move on to this. Not this one. More two. Okay, you've seen this. So this is kind of some thing is repeated. What's a property? So given this, it's a set of acceptable infinite behaviors. They can be either linear traces, or you look at, define them as set of traces, or a computational tree of traces. So linear time property, a property is a constraint, okay? It denotes a set of paths. Okay, so example is the set of paths in which eventually AB, the paths should be such that at some point in the future, eventually AB will be equal to 0, or you can have branching property as we have done this, okay? So like you said, we'll be looking at, we'll be starting with CTL star, and we'll also be looking at some specialized sublogics. You will see that these, the model checking problem for the sublogics are less complex than CTL star, okay? Okay, so this is a temporal logic, CTL star, which is capable of expressing a class of properties, both in linear time properties, as well as branching time properties. Okay, that's what I'm going to be introducing. So anytime we introduce logic, just like we saw, which you already seen in your logic course, and you saw when we introduced propositional logic and quantified Boolean logic, we first introduce the syntactic components of the logic, and then we define the semantics of that logic, okay? Syntax defines how you construct valid, well-formed formulas in that logic. Semantic tells what assigns meaning, interpretation to the various syntactic components, and says what it means for a particular formula to be true or to be satisfiable in a particular model. So first we will introduce the syntactic components of CTL star. Okay. There are two kinds of syntactic components: state formulas in CTL star, state formulas and path formulas. Okay. The state formulas are constructed using path quantifiers. Okay, by the way, as I've actually noted, all this is the subject matter of chapter 4 in the reference textbook. Okay. So it's denoted as A for all. So a state formula, informally, it is true of, meant to be true or false of a particular state. So you construct, using path quantifiers. If A is a universal path quantifier, then, and if phi is a path formula, we will introduce how to construct path formulas. A phi is a state formula. It is true of state S informally if every path originating from S, from the state S, satisfies the property phi, where phi is a path. A path formula is true or false of a path. Similarly, E phi is a state formula. It is true of a state S if there exists a path from S that satisfies the path formula phi. Now, the path formulas that are part of CTL star are themselves constructed using what are called linear temporal operators. Okay, these define path formulas. Okay, I'm using formulas and properties interchangeably here because a property will eventually be expressed as a formula in CTL star. Okay. So linear temporal operators. Okay, these are some of the operators that you see. Sometimes the OR operator is not is not introduced. It is used as a derived operator. So there's an operator called X, which is called the next time operator. Okay. So all these are, if P is some path formula, XP is it's a path formula. These X, F, and these operators construct, all of them construct path formulas, okay? And they are meant to be true or false of a path, okay? So here I'm defining something, as I introduce the syntax, it's informal meaning. So X of P is true of a path. All path, I mean infinite paths, okay? Because those are the kinds of behaviors that we are interested in. So it is true of an infinite path or trace. I use path and trace interchangeably. If P is true in the next state, actually, I should be introducing one thing. So if P is just a predicate, that is also a path formula, okay? Just a predicate, a P. So, it is true of a path if it is true in the first state, okay? This is kind of a special deal, okay? So, usually when you have a label or a predicate, it is meant to be true of a state, okay? So, but we will also make a state formula as a path formula in this special case, okay? This is true of a path if it is true in its first state. XP is true of any path, any trace, in which P is true in the next state, the state next to the first state on that path. Now, FP is true of all paths, of any path, in which P, by the way, here P is any path formula, okay? These path linear temporal operators, they construct path formulas from other path formulas. So P and Q here is to be read as other path formulas. This is the special case in which a state formula itself can be interpreted as a path formula if it is true of the first state. So FP is true of any state if P is true at some point in that, at some future point in that state for I greater than equal to 0. So G of P is true of any path in which P is true at every point in that state. So similarly, P until Q is true if P continuously holds up to the point when Q becomes true. Okay, and this is called the release operator, which says P releases Q, which is kind of the dual of the until operators. The until operator says Q must eventually hold good at some point, and P should hold good all the way up to the predecessor state at which Q will hold good. Whereas P release Q is true of any path as long as Q is true up to the point when P becomes true, after which you don't care whether Q is true or not. Okay, so these are something, but the point is we will define more formally what the semantics of these things is. But the important thing to consider here is these are operators that construct path formulas from other path formulas. And the way that you construct state formulas, two important ways, is that using these path quantifiers, the universal path quantifier, existential path quantifier. Okay. And of course, a predicate by itself is a state formula as well. Okay, now here, okay, given these operator introduction, here is the formal syntax of CTL star. If P belongs to one of the atomic propositions, then P is a state formula. Okay, because after all, an atomic proposition is true of a state if that label P belongs to that state, or P is true of that state, as we have interpreted. So an atomic proposition is a state formula, is an atomic state formula. So F and G are two state formulas, two arbitrary state formulas. Then you can apply the usual logical connectives, not, or, and the conjunction operator to make bigger state formulas. So as we have seen in the previous thing, if F is a path formula, then you can construct a state formula by applying the path quantifier, existential path quantifier A, to get a state formula. And then there are rules to construct path formulas. If F is a state formula, then F is also a path formula. Okay, and as I informally said in the previous slide, this is true of those paths in which F is true of the first state. Okay, on that path. Another way, of course, if F and G are path formulas, then you can use the usual logical connectives to construct other path formulas. And you can, additionally, you can use any one of those temporal, linear temporal operators that we show. This is called the next time operator. This is the eventuality operator. This is the, forever operator until and release. Okay. So CTL star is defined to be the set of all state formulas. So at the top level, you require a CTL star formula to be a state formula that is permitted by the above inductively defined rules. Okay. Any questions? We will see some examples, later on. But you have any? Okay, no questions? Okay, I'll move on. So let me get you an example to understand what state formulas and path formulas are if you're a little bit puzzled. Okay. So given this system, and this is one of the branching behaviors. So since there are two initial states, there is another branching behavior here, with starting with this initial state, 0, 0, and with the reset being 1, which I have not shown here. Okay. So this formula, this atomic formula that says AB is equal to 0. Is this a state formula or a path formula? As per the rules that I described in the previous slide. I have two kind of
State formula, because it's part of AP.
Yeah, it's certainly a state formula, but I've also said in rule P4, if F is a state formula, F is also a path formula. Since this is a state formula, so intuitively this is obviously a state formula, because you can tell if it's true of a state or not. But the way we have defined the syntax is every state formula is also a path formula. Okay, so it is also a path formula. So intuitively, a state formula, which is also a path formula, is true of a path if it is true in the first state. Okay, that's the convention that we will use to make a state formula also have meaning as a path formula. Okay, so here my questions are only about the syntactic aspect. I will get to the semantic aspect very soon after I define the formal semantics. So this one, which is constructed from G is equal to AB is equal to 0.
It's a path formula.
Yeah, it's a path formula. Correct, because it is a Y.
AB equal to 0 is a path formula, then G of a path formula is also a path.
Yeah, I mean, this is first of all, it's a legal formula because it's constructed by applying one of the linear temporal operators. Okay, so it's because of this rule. This is the way path formulas are constructed. Okay, so you can use here they're using G on a. And since you have to use its subformula, will have to be, this has to be applied only to a path formula. But since AB is equal to 0 is also a path formula, it is a well-formed path formula, but it is not a state formula. Okay? Because the only way you can construct a state formula, you cannot use, it cannot be by using a linear temporal operator. Okay? Yes? Erumalai?
He'll restart. His router has issues. He'll restart and join again.
Say that again?
His
Yeah, he
router
has
is
some-
having issues. He will restart the router and join the meeting again.
Or this is Ratnakar, is it?
Yeah, I'm Ratnakar.
Okay, should I wait for you or shall I go ahead? I'll go ahead.
No, not me. Palamalai will do that. Like you asked.
Oh, I see. Okay, then question is for Amin.
This is also path formula, right?
Ah,
Similar to the G of.
Yes. Similar to that. So Ratnakar?
This is a state formula. X before anything makes it a state formula.
No, X is a temporal operator, no? It's the next state operator.
Okay.
So this is a path formula, but it's not a state formula. Okay? Because whenever you use a linear temporal operator to constructing, that is always a path formula. Yeah? And it has to be constructed from a path formula. So since, it's the subformula G applied to AB is equal to 0 is indeed a path formula. So it's a well-formed path formula. It's not a state formula. So I guess Paramalai is back. So I'm asking this question individually, Paramalai. For each of the formula that I've shown, I'm asking the question if it is, I'm asking you to tell me if it is a state formula, a well-formed state formula or a path formula. Is this, what do you think? Is this a state formula or a path formula or both?
It's a path formula
Yeah, why so?
because AB is equal to 0, that's a state formula. And
That's not the reason, because how is it constructed? By applying X to a linear temporal operator to a formula, a subformula, which is, okay, firstly, AB is equal, okay, what is the subformula? This once again for
so
Paramalai.
the subformula is a state formula.
Subformula is a state formula. But a state formula can always be, it also can be used, can be used as a path formula, okay? Remember, that's what we said. Therefore, when I'm using X, I'm using EG of AB is equal to 0 as a state, as a path formula, because a state formula can always be interpreted also as a path formula, okay? And therefore, this is by virtue of the fact that it is being applied, constructed using a temporal operator, and its subformula can be is a legal, can be construed as a legal path formula. This is a path formula, but not a state formula.
This is both state formula and path formula.
This one is certainly a state formula because you're constructing using the E operator. Okay. Did you say it is also a path formula? Did you say that? Who was that?
Yeah. Formula, sir. Because we saw that every state formula is also a path formula.
Ah, that's right. Okay. It is a state formula, but I've left it is a path formula. But since every state formula can also be used as a path formula, so you could, I guess.
Sir, could you repeat why we distinguish between state formulas and path formulas?
I think the distinction, why do we distinguish? Okay. I mean, you could see the subset of the path formulas later on. No, because if you want to talk about branching time behavior, how do you, I gave you a lot of instances of the kind of behaviors that I want to talk about. Okay. Since if I want to say that from every initial state, there exists a path on which there exists a path that satisfies a certain path condition. How would you state it? So if you want to state that something about, see, that is how the branching behavior is stated. Okay. So in order to be able to do that, you want to say that, oh, every path that is originating from a particular state has a certain pattern. Okay. Is of a certain, has a certain pattern. Okay. Therefore, you need both. Okay. This branching behavior is, whereas linear behavior is only constraints on paths. Okay. And therefore, so you need be able to say path formulas. Okay. So that is, you need constraints, and branching behavior is a combination of constraints over on states and the constraint on states is stated in terms of the kind of paths that are allowed to originate from those states. Okay. And that's why that you have. Now, if you're only interested in linear time behavior, then they are constraints only on paths. And you will see that if you restrict yourself CTL star to only linear temporal or path formulas, the subset of path formulas, then you get the LTL. You get LTL, which is the thing. And that's why you have both. Okay, since we want to be able to CTL star is a language that is meant to describe branching behavior, which also, by the way, includes linear time behaviors. Okay, as the thing, and that's why you need to be able to state not only conditions on paths that describe the kind of patterns on paths, as well as be able to say something like the paths originating from things all satisfy certain conditions, certain path conditions, or there exists some paths that satisfy things. Okay, so that's why they're being. Now, why restrict yourself to just? Obviously, it is restricting yourself to certain kinds of rules, which are stated in terms of operators and so on. I mean, they are motivated both from the point of view of they're interesting. They're interesting because they're able to express, when you design a language or even a specification language, two constraints have to be satisfied. One is they should be able to specify interesting class of properties. Okay, and they're guided. The design is guided by that consideration, as well as another consideration. How am I, by putting certain restrictions, can I make the my task of checking whether a particular model satisfies the property in a reasonably efficient way. Okay, these are the two guiding principles. Anyway, I mean, your question was, why do you have two kinds of formulas? And that is, and I hope I have answered that.
Yeah.
Okay, how about this? This one is for, who did I ask? Now, Amit, yeah?
This is also a state formula, right? Yeah, I think so. Because E of something, but I'm not sure whether the thing inside is.
Yeah, you see? So you have to look at look at the subcomponents. So this is a disjunction of two subformulas, okay? What is the second subformula of second disjunct? The one that is starting at G. Is that a state formula or a path formula?
Yeah, that is a path formula.
That's a path formula, correct? Therefore, if it's a path formula, yes, the first component can be a state formula, and so it can also be a path formula. So here you are, your rules are saying either you can take a disjunction of two state formulas or two path formulas. So this is well formed only if you interpret the first part as a path formula. Okay, so that this can serve as a path formula as well. Since the second component is necessarily a path formula, this one is a no, this is actually wrong. This should be,
no, it will be a state formula, right? Because at the end, E of the whole path formula is taken, right?
I'm sorry, I misread the parentheses. Okay, E is applied to the parentheses. Here is the parentheses, the outer parentheses extends all the way to. So this is a state formula. I'm sorry. So yeah. But if you had this parentheses ending here, okay, instead of here, okay, after the first disjunct, then that would be a path formula.
Yeah, yes.
Okay, so now formal semantics of CTL star. So let's see what the time is. Okay, I still have 10 minutes. So let me first just define the formal semantics. Okay, how do you define the meaning of this thing? So you have to say that given a model, which now is a Kripke structure, and a state and a path in it, that's how we define whether a particular, because we have two kinds of formulas here. One, state formulas as well as path formulas, which are nested inside each other recursively. So the meaning, that is the truth bound of the interpretation, is defined relative to given a model, a Kripke structure, which has a transition system and a labeling function for states, and a state and a path in it. This tells whether a thing is satisfied or not. So for path formula, you require a model and a path in it. Then you define whether a path formula is satisfied by this Kripke model and given a path in it. And similarly, for a state formula, the satisfaction relation is defined as given a state, if the state formula is true of that state in that model. Okay, and you will see that a state formula, the meaning will be defined in terms of its the meaning of its sub-formulas, which could be other state or path formulas. So this satisfaction relation, like in propositional logic or like in any logic, will be defined inductively. volume. Okay, before we show that, I will define what the formal problem statement. You've already seen, but the model checking problem of CTL star is one of checking given a Kripke model and a formula in CTL star, which is defined, okay, although a CTL star formula, a well-formed formula, can have subformulas which are path formulas. At the top level, it is defined as a state formula, okay? Therefore, this is how, okay, the model checking problem of a formula in a logic is always defined whether a particular model, Kripke model satisfies it. So, since it's a state formula, it is defined as for every, it is an M model satisfies a formula, a CTL formula psi, if for every initial state in the, for every state in the initial set of states, initial condition, M comma S satisfies psi. That is, every initial state should satisfy in the model, should satisfy the formula. And that's how we will define it. Okay, so we define it inductively. So here we assume that F1 and F2 to be denoting some arbitrary state formulas, G1 and G2 to be path formulas, and pi is any infinite path, and pi I means for any I greater than or equal to 0 denotes the suffix of the infinite path starting from index I. That is, if you remove 0 to I minus 1 positions on the path pi, the rest of the path, the prefix starting from 0 to I minus 1, and you remove that, that is what pi I is meant. Okay. So first we give the meaning of all the state formulas. So P is the atomic predicate. That is the base case. That is true of a state in a model M. If P is, if the label, if P, the label, if P is a label belong to S, that is, P is true, the atomic proposition is true of that state. Then the negation and or are defined as per the standard meaning of the logical connector. Okay, so not of F is true in a state inside a model M if it is not true in if F1 is not true for the same state, and similarly if or and. Now the real interesting stuff starts with E. So this is defined as it is true of a state S in a model if there is an infinite path pi, a legal infinite path pi starting from S, such that the path pi in that model M satisfies the path formula G1, the path subformula G1. Okay, so that's how it is defined. And so similarly, AG1 is true if it is true if every infinite path starting from S satisfies the subformula G1 as per the satisfaction rules for path formulas. Okay. So the path formulas are defined for recursively in terms of the meaning of the interpretation for sub path formulas. So M pi, so X of G1 is true of M of pi if and only if G1 is true. G1 is a path formula, remember? It is true of the path that you get starting from the suffix 1. pi. Okay. So it says that it's true of a path pi if we remove the first state, take away the first state, and then keep the infinite path, the suffix infinite path, then G1 must be true of that path, and that's how that you define. Okay, so remember that the path formulas are constructed from other path formulas using linear temporal operators, and therefore they are defined recursively in terms of for a path in terms of the suffixes of these the paths. So f f of G1 is true for a path n if there exists a k greater than or equal to 0, a future point on the path at which G1 itself is true of the path starting from, is true of the path of the suffix path starting from k. Okay. And this defines the meaning of the forever operator. Then this is true if it is true for every suffix, okay, of it is if the subformula G1 is true for every suffix of for every suffix that you get from every position in that path and so on. Okay, so similarly, I will do. So there is one thing that is missing here. Since a state formula P can also be a path formula, so there must be one rule for when you use that. Okay, so if it's a state formula, then that is true of m of pi. I think it should be there as well. I mean, if it is true of pi of 1, okay, not pi superscript of 1. It is true of the first state of that of that path. Okay, that should be there as well, because a state formula it can also be interpreted as a path formula, and therefore there must be a rule corresponding to describing that. Okay, and that is m of pi is true of just a state formula, say P, if it is true of the first state of that path. So G1 until G2 is 2. There are two conditions. If there exists a k greater than or equal to 0 at some future point, G2 must be true. That G2 must eventually hold good of that path starting from the kth suffix, the suffix path starting from the kth position. And for all prefix between 0 and k minus 1, yeah, from there the pi j, pi j, the suffix that you get from that position, G1 must be true. Okay, so that is how it is. It's defined. So similarly, the release operator is defined. You expect G1 to be G1 releases G2. So G2 must be true up until the point G1 is true. So this is how it is. It's defined. What I want to stop here, but what I want you to do is in the next class we will go through some more examples. But in the meantime, what you can do is look at just interpret these formulas that I showed you here, if they are true or false for this particular model, Kripke model, as per the rules that are defined here. Okay, so just go through that exercise yourself. Okay, I'm saying just use these things, these formulas, and then come up with your answer. If it is true as a path formula, if it is true of any path in that, and when it is a state formula, if it is true, I mean, come up with some states in the system, in your branch behavior for which it is true. Okay, so, or if it is true of the initial state. So we will discuss that in the next class. Okay, so any questions?
So you said every every state formula can be a path formula, right?
Correct.
So how do you interpret a path formula that says E something?
I don't know.
I don't think that was covered in the semantics slide.
Yeah. I think I have to be careful here. Okay, I think no. See, I mean, how exactly CTL star used, I have to. I will be careful. So I'm interpreting it as if it is true of the first state. When you interpret a state formula as a path formula, it is true of any path in which that state formula is true of the first state.
Yeah, okay.
That's how it is interpreted. Okay. Then so you can have a state formula of the So that's how it is interpreted. So that can be a complex state formula, or it can be a simple atomic state formula. Yeah. It is true of a path if it is true of the first state. That's how it is interpreted. So then you can apply the rules of existential quantification, etc. I mean, even as existential quantification. Yeah. It must be true of the first state in that path.
Okay.
Yeah, that's how it's defined. Okay. Any other questions? Okay, if there is none, then I'm going to stop sharing. There's some chat here. Okay, that's old.